University. Betsy's giving the presentations.
Okay, so I'm Betsy, and we're going to be talking about quantum dynamics of nonlinear oscillators. What we were researching was motivated by Josephson junctions, which is a commonly studied tunneling junction. And the reason that we're looking at the quantum pendulum is because the equations for Josephson junctions and the quantum pendulum are analogous. So we were going to be spending this talk looking at the pendulum. So first we're just going to start by looking at just a regular pendulum. It has a bob of mass m, rod of length L, attached to a massless, that's massless. Cannot come up with the word, I'm sorry. Drum, there we go. Thanks. And it has a torque which is caused by this block of mass m, and so that's causing driving, and then it's in a viscous medium, which is going to cause damping to the system. And it has a gravitational potential energy, and we're going to be focusing on this angle. So, but the Josephson junctions that we're interested in are in the quantum limit. So we'll be working with the quantum pendulum, and so we have to use Schrodinger's equation. Now, you might notice that my Hamiltonian here has a bar over it. Now, this is notation for the fact that we have not yet scaled the Hamiltonian, and so it is not dimensionless yet. So it's every time that you see a variable with a bar over it, it has not yet been made dimensionless. So we have a little bit of trouble solving the Schrodinger equation analytically, though, due to our potential energy function. And there's a graph of that there. And except in these two limits. When our total energy is small, the potential energy of the pendulum is very similar to that of a simple harmonic oscillator. So we can then have results from the simple harmonic oscillator to test what we're doing. And if the total energy is large, then we can treat it as a rotor, which you can also solve analytically, and so we can have results from there. So how are we going about doing this? First, we looked at the driven quantum pendulum. So we had to solve Schrodinger's equation. And this is our Hamiltonian, where we have the kinetic energy, the potential energy, and our DC driving torque. And you notice our L bar is actually an operator. And then we made everything dimensionless. We scaled the energy by h bar squared over 2I, and the time by h bar over 2I. And so this is our new Schrodinger's equation in dimensionless form. And we needed to start with an initial wave function, and we chose a Gaussian. Our parameters that we can change for this is sigma, which has to do with the width, the center, where the Gaussian centered about, and our initial angular momentum. For our system, we chose sigma to be 1, have it centered at 0, and have an initial angular momentum of 3. So what did we actually do? Well, we start with our initial wave function in position space. We then do an FFT, which is a fast Fourier transform, to change it from position space to momentum space. So now we have a phi of f and eventually tau, but at the moment it's just our initial. And then we solve Schrodinger's equation numerically using fourth order Runge-Kutta method. And then we get our phi of f and tau. And our f is L over 2 pi. So that's the same L from before. And we use our phi then to calculate our expectation values. The ones that we're interested in are the expectation value of the angular momentum, kinetic energy, potential energy, and total mechanical energy. Just a note, when we're calculating the expectation value of the angular momentum, our L is a number and not the partial derivative that we saw previously. So here are some graphs from just having the gravitational potential energy. We aren't driving it or damping it yet, which we will get to the damping part. This is a graph of the expectation value of the angular momentum versus our dimensionless time, tau. As you can see, with the u naught of 0, so our gravitational potential of 0, we can treat it as the rotor. So the expectation value of the angular momentum is constant, and then as our gravitational potential increases, it is approaching the limit of the simple harmonic oscillator. So as you can see with the u naught of 10 and of 25, it's oscillating more. And if you notice, this is a graph of the total mechanical energy versus tau, and the energy is constant as we would expect, with no drive and no damping. Now we're going to add drive to the system. This first graph is again the expectation value of the angular momentum versus tau. This is for a fixed drive, gamma is 2, and we did this with increasing values of our gravitational potential. So as the gravitational potential increases, the slope decreases, and it also becomes more oscillatory, like we would expect based on the values of u before in the previous graph. Now, if instead we fix our gravitational potential and change the value of the DC driving torque, then we will see that as that increases, the slope of the lines increases, and there's a little bit less wiggle between like this one and that one, and then finally the last one with the driving of 2. Yeah, it keeps switching on me. It really does not want to be on this page.
Wow.
Like, really does not want to be on this page.
What is that? This is hold it?
Nope.
Office or something.
Yeah. Worked before.
That's a good idea.
Yeah.
Just do that.
Okay, we'll just do it this way. I don't know why it doesn't like this slide, but it doesn't seem to. So now we need to add our damping. So we're going to use the quantum state diffusion method, which is studied but kind of complicated.
It doesn't work well.
Yeah.
That's probably gonna jump on me again. Go check.
Yep. So you got a preview of the last two slides a couple times. Okay. So we'll just say this. Okay. So we're adding 2 operators now that we're going to call that are Lindblad operators, and we are going to call them L1 and L2. L1 is used to displace the angular momentum downward when the angular momentum is positive, and L2 displaces the angular momentum upward when the angular momentum is negative. And so this is our new equation. We have the same Hamiltonian as we had before. Then we have this deterministic term for the damping. And we also have this stochastic term for the damping, which means that it's random. And this is our random variable for the 2 different Lindblads, and they're Gaussian distributed random numbers. So the way we went about doing this is very similar to what we did before. We just start in momentum space with this Schrodinger's equation. We then solve it numerically using 4th order Ramicutta, and that deals with the deterministic part of the damping. Then we get our phi of f and tau. Then we need to add the stochastic damping term, which gives us our total phi. And then because of the randomness, we have to average multiple trajectories of this, and then we can calculate our desired quantities, which are the expectation values that we talked about earlier. So here is a graph of the results. We have this new variable, kappa, where our 2 Lindblads are proportional to the square root of kappa, and so that's our dimensionless damping constant. In this graph, the initial angular momentum is 3. So all of them start at 3. And then dependent on the amount of the driving, so for driving of 2, it's the highest up and actually ends about 2. And then it just continues down, and the damping has a stronger effect as the driving decreases. And if you notice, over a long period of time, it seems to sort of settle down into a steady state behavior. And this is going to be important because we are going to use that to do the time average of the expectation value of the angular momentum. And in so doing, we did this with different values of the driving torque. And so the blue one has a kappa of 1, and the red one has a kappa of 1.5, so our damping. And for the stronger damping, the slope isn't as steep, which is what you would expect based on that. So we've started working on this is trying to couple 2 quantum pendula torsionally to see if we can get them to synchronize. And one way that we can check for synchronization is using the expectation value of the Kuramoto order parameter, shown there. And actually the first thing that we will do is we'll use the time average of the expectation value of the angular momentum for each of the pendulums and see if based on the coupling constant, if we can get them to converge at some point and therefore reach synchronization. So I'd like to thank Dr. Trees and all of the other professors and National Science Foundation for this.
On your results for the damping, not
This
that
one?
with the previous one.
This
yeah.
one?
There are sort of like, almost like steps. Do you have any sense, maybe the purple one is a good one to see, where it goes down and then it drops a second time. Do you have any sense of why that, what that is that's causing it?
One thing that we did run into was we have a certain number of basis states, like a number of things that we're looking at. And if we increase that, we saw less of that happening. At first, we had that too low. And for the smaller values of the damping, it would just, of the driving, it would just stay at, it would actually just stay there, while the other ones would actually drop down. So we increased that, and it also may have something to do with the connection between the damping and the driving and how that works. But increasing the number of basis states may decrease that, the noticeability of that as well. Yes.
Could you talk about the analogy to the Josephson junctions a little more? What more parts and things you've seen here might be expected to show up in the junctions?
Because their equations are analogous, we're expecting, the expectation is that if we can get quantum pendulum to synchronize, that then it's also possible to get Josephson junctions and the quantum limit to synchronize. And that's sort of the goal, is to get that to happen. Did that answer your question?
Yeah.
Okay. Sean?
What exactly is a Josephson junction?
It's 2 pieces of superconducting material, and in the middle is a piece of non-superconducting material. And if the current going through them is small enough, then there's no voltage drop across the non-superconducting material, meaning that it all acts like it's superconducting. But if the current going through them is too large, then there will be a voltage drop across